This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good afternoon. I brought this toy. So some of you in the lab, you will be playing with this one. So I just brought it for you because someone asked me if they're here, raise your hand. Someone asked me to explain about the assignment. What is alpha, beta, gamma, and delta, roughly. So there are two parts. Yeah, I can disassemble. Now this is the rotor, but in your assignment, the rotor is without these two sticks. So the two sticks here are like in the assignment modeled here. Okay, but just think of these two as two rigid bodies. Okay, they can have motion one relative to another. And this is the frame. Okay, this is the frame. This is the rotor. Okay, so in, I think it's figure 5 or something like that, you are only shown the frame of the gyroscope, like the housing, in different views when it is like that. So points A and B are somewhere on the right and the left. I don't know what you can see. Yeah. So essentially, angles alpha, beta, and gamma, they define the orientation of the frame of the gyroscope. Yeah. When I say frame, I don't mean now coordinate system. I mean this part. Okay. So something like alpha, beta, tilt, and gamma, final rotation. So these alpha, beta, and gamma are needed to define the orientation of this 3D body in space, the orientation, okay? On top of that, this rotor, if it's inside, I need another, because there is just one axis about which it can rotate relative to the frame. So I need another, let's say this is the orientation of the frame of the gyroscope. I need another angle to define the orientation of the rotor relative to the frame, and that would be the use of delta. Okay, so delta dot is kind of this thing. Okay, alpha, dot would be the precession, beta dot would be how much it tilts over time, and gamma dot how much the frame rotates. Yeah, the frame rotates like this. Well, think about it, or ask me, or play with it in the break. Don't steal it. Let's go back. Yeah. Okay, so we were talking about linear momentum. I need to adjust here to the two different screens. All right. So for linear momentum, let me just say a bunch of things. First of all, we assume now point O is a fixed point. All right. Why is that? We are going to relate P, the linear momentum, we are going to relate it to the sum of forces acting on the rigid body. And in order to do that, we are starting from Newton's second law. So we are utilizing that law, which has absolute acceleration, absolute linear acceleration. Okay? For absolute, we need a fixed point. Let's concentrate, because it's a major area for mistakes. Okay? Calculating linear momentum relative to a point which is not fixed is a common mistake. So pay attention. So what we are doing in this slide is where I stopped. We are, instead of doing the integration, after having found the center of mass, especially if it's a rigid body where it's obvious where the center of mass is, say this one, it's obvious where the center of mass is. We don't need to do the integration every time from scratch. We can just use this linear momentum. Pay attention to the definition. If I ask you, what is the linear momentum of this rigid body? Okay, don't be lost. Look for a fixed point. Look for the center of mass of that rigid body. Look for the absolute linear velocity of the center of mass, okay, and multiply by the mass. So this would be the linear momentum of the rigid body. All right? How to get from the definition to here? What do we do? Do you see how this is the definition? Summation over the linear momentum of each kind of mini particle within the volume. Okay, so what I'm doing here, I'm splitting the vector from O to some point P, that point that travels across the rigid body. I'm splitting it to OG plus GP. So this is the slide we were dealing with. So let's say if this is point G, yeah. So this vector is simply this plus this. OG plus GP. Okay, so for every point P, instead of going directly OP, I can go OG plus GP. Okay, why do I do that? So that I can cancel the contribution of just this one, RGP dot. Yeah, as according to the property that I mentioned last lecture. Okay, and then finally I'm taking this value ROG dot outside the integration. Why can I do that? I'm integrating, I'm moving across the volume. So I'm changing point P, essentially. Point P is moving. Okay, so rho P changes. But ROG dot is constant in the integration. Not in time, but across the volume. It's the same O, it's the same G. Okay, so as I'm moving with my point P, ROG dot remains the same physical quantity. Okay, so I can take it outside of the integral. And then this integral is just integration over the infinitesimal mass of each such mini volume. Okay, so I'm summing all of these mini masses. I'm getting the total mass. Okay? Okay, so are you comfortable with this definition? What we are going to do now is to take the time derivative of this. Okay, so P dot equals M R O G double dot, time derivative of this, and relate it to the sum of forces. So we are going to, let's see if I wrote this equation. Yeah, so if you remember this one here, so just this part is the time derivative of what's there, okay? And we are going to show why it is equal to this based on Newton's law for a particle, okay? Okay, so okay. So P dot, I'm going here by the definition from here. Look at this one here from the definition. Integration over particle. This is over, sorry, like a bunch of particles comprising the entire rigid body. If you look at the time derivative of this part here, oh, you can't see. Why are you quiet? You can't see the pointer. You imagine, you read my mind. Cool. Okay, looking at this part. Guys, don't be shy. I'm from Israel. We are annoying people. So, look at this. Take the time derivative of this. So P dot equals our integration over acceleration of these points P across the rigid body times their mass. Okay, so this is it. Okay, now how do I jump from here to here? So this is where I need your attention. Okay, so let's say this is the rigid body, and I split it to these cells. And each cell, yeah, is this volume dV, okay? So if I take this one out to look at, it has forces applied on it, okay? So this is, you can look at it as a particle. If it's small enough, it's like a particle. So let's look at the forces that are applied on this piece of volume, dV, okay, dV. Now, there are external forces. Okay, I'll put them in blue. So, external forces, like what? Like gravity force, which is, it comes from Earth, so it's external to the rigid body. If someone comes and presses on that point, yes, someone external pressing on that point, So you can imagine external forces and internal forces, which are interactions between the neighboring particles within this volume. Okay, so in addition, I'll just draw. Can you see the color difference? Yes. So internal forces. Okay. But then for every internal force, every green one, I have the opposite direction, same magnitude, on one of the neighboring particles, right? So I can draw, say, this one here. Let's say this is number one, and number 2, dv, 2, so this one. Maybe, say, if this internal force came because this particle presses on this one, then this one presses on this one with the opposite internal force, right? And every such internal force has its reaction within the material, right? Within the same rigid body. Okay, so as I'm looking particle by particle, yeah, I'm summing all of the forces, both internal and external. But as I'm doing one big sum, all the internal forces will cancel out. This is what I'm trying to say. All the internal forces will cancel out, and I'm left with only the sum of all the external forces on the rigid body. Now, why do I sum that? We are doing this. So looking at P dot, this is equal to integration over the volume of the rigid body, R double dot OP, so our double dot, which is acceleration. Think of A in your Newton second law. Acceleration, actually absolute linear acceleration, absolute linear acceleration. Whenever I need to write acceleration, I decelerate my lecture. So long. So, and then rho p dv, which is mass. So this is of point P, and this is of point P. Okay, so it's like m times a, ma. Okay, ma, according to Newton's second law, is the sum of forces on that particle, right? So this is, according to Newton's second law, sum of forces, all of these forces. Okay? And because I'm integrating, I'm collecting all of them. I'm collecting the green and the blue. Okay? But throughout the integration, the green ones, the internal ones, will cancel each other. And so I'm left with a summation over all of the blue ones, all of the external ones. Okay, so overall, this will be equal to, let's say, maybe I'll expand that. Sum of f, let's say, I put it here as d sum, as this d kind of for just a particle, all the forces on the particle. So external plus d sum f internal. Okay, so this is the green and the blue. Okay, so these ones will cancel out. Oops. Cancel out throughout the integration over the entire rigid body, and you will be left with the sum of all of the external forces, and that's the resultant force acting on the rigid body. We'll talk about that one later, but overall, this is the resultant, or the overall, like the sum of all forces, yeah? Force acting on the rigid body. So only external one. Okay? This one survives. Okay? So this is how we go from Newton's law for a particle, this, to the rigid body one, containing many such particles, a continuum of such particles. Okay, so this would be the sum of all of these blue arrows, all the different applied forces on the rigid body. You sum them in the same way you summed forces in any mechanics subject. Yeah, it's just that now it's not 0, it's p dot. Okay, so this is the linear, can you see? Yeah, this is the linear Newton-Euler equation. All right? Any questions? So for, you sure guys, no questions? This would be the linear Newton-Euler equation. Okay? Now, some examples, just basic 2 examples to give you the sense of what you will be doing to construct Newton-Euler equations. So far, we've been preparing that p dot, right? We know how to calculate the linear acceleration, right? So we've been preparing that p dot, okay? Later, we'll be preparing the sigma f part, okay, and combine them all together. So when you are told to write down the linear Newton-Euler equation for a given rigid body, you need to know what to do. Okay, so you need to find the center of mass of that rigid body and the absolute linear acceleration of that center of mass. Okay, and that should be equal to the sum of forces on that rigid body. So here we have 2 rigid bodies, 2 links. Okay, assume that G1 and G2 are the respective centers of mass. Okay, and now we are going to prepare these linear Newton-Euler equations for each of the rigid bodies. Now, this red frame is attached to this link, but you can write this equation in any frame you like. Okay, you are not constrained to any particular frame. Okay, because this sum of forces is a vector. This acceleration is a vector. You can write these vectors in any frame you want. Okay, I'm chewing this sentence. Same for this one. Sum of forces on this link, you can write in any frame you want, as long as both sides of the equation are in the same frame. You can equate them. Okay, but you can write this equation in different frames, and in those different frames it will appear slightly differently, but it will be equivalent information. Okay, now these are vector equations. Okay, so remember, this gives you 3 components. So 3 scalar equations and another 3 scalar equations. All right. Now, why point A, not O? I said we need to have a fixed point, right? But in this example, A is a fixed point. Why? So I defined long time ago. Assume in this problem, A is a fixed point. Okay? Any questions regarding the construction of these equations? So all we have to do is just decide in what frame do we want to write these equations and find out what is our double dot here, what is our double dot here. Okay, and this is things that you know how to do at this stage, right? So I've prepared the absolute linear accelerations of G1 and G2. You can have a look, you can calculate to check. Any questions about that? Okay, and then I'm multiplying by the respective masses of the links, and this is P1 dot. Okay, so time derivative of the linear momentum of this first link, and this is the right-hand side is P2 dot, the time derivative of the linear momentum of this link. Okay, now the left-hand side, the sum of forces, I'm leaving aside. We'll do that later. So remember these examples, and we'll come back to them. Just sum the forces. But first, we will need to do free body diagrams. Okay, but so leave the left-hand side for later on. This is the other example. Okay, again, write down the linear Newton-Euler equations. In the last exam, I think, in 2018 dynamics exam, I wrote, please write, without the please, write the Newton-Euler equations. And instead of writing, I'm a bit confused. I asked for the equations of motion. And people wrote down the Newton-Euler equations. So I just want to make you pay attention. This is not the same. Okay, when I say Newton-Euler equations, I mean for the linear part, it's the sum of forces equals P dot, the derivative of linear momentum, and for the angular part is sum of moments equals H dot, the derivative of angular momentum. I will elaborate on that. The second part is not quite accurate. But just distinguish between Newton-Euler equations and later when we talk about equations of motion. It's not the same thing. Okay. Now for this example, it's pretty much the same. Okay. You can see here for the vertical link, because the center of mass of the vertical link is fixed, it's stationary, it has no linear acceleration despite it rotating. We have this equation, which is like what you would do in statics, okay? And this one, you can check it. Just check the linear acceleration of the center of mass, not the end here. Just maybe look at what we did before. We found ROC double dot. So how to move from ROC double dot to ROG2 double dot? Just replace L by L over 2, okay? And you should get that. Any questions? Any questions about this lecture in general? Okay, so I'll wrap it as what we were doing. We looked at, sorry. Let's say Newton Euler equations. We looked at the linear part. Which is sum of forces equals P dot. Okay, we defined this P. Okay. We looked at P for a rigid body as the mass of the rigid body times the absolute linear velocity of the center of mass of that rigid body. Okay, so we defined linear momentum and we did this equation. Okay. And now we are going to move towards sum of moments equals h dot. Yeah, but we are doing it about the center of mass, which we are already familiar with. Yeah, we covered the center of mass formula. And what we are going to get on the way is this kind of I omega that you are roughly familiar with about point G. Okay, so I'm going to elaborate on why that thing is okay, again based on the same Newton law for a particle. Okay, this is our starting point for all of that. Okay, so Newton-Euler equations are these ones. For this one, we will have some variations. In addition to this one, we'll have some special cases or other variations for that. But overall, the reason we write down these equations, from them we'll be able to extract equations of motion, and these ones are those you go and integrate and get the prediction of the motion over time. Okay? So this is where we are going, roughly. So let's move to the other lecture. Okay. So in this part, this lecture, what we are focusing on is defining H about the center of mass. And now I'm using the top right corner. Okay, so I'm having so many different corners of a letter. Okay, if you forget the meaning of something, let me know. Okay, I will explain. So top right is about which point? All right, here it's relative to this point. Okay, relative to this point of this point. Okay, and this is about this point. Okay, so just a little bit. Yeah, so be prepared. Be prepared because we are doing a lot of integrals. It's going to continue a bit more. Just be patient. We'll finish with all the integrals and we'll get a simpler form as I showed you here. So we have some route to go from this, yeah, to this. Okay? And so just be patient with the maths. Okay. So first, let me start with the definition of angular momentum. So this P is linear momentum, and angular momentum. And essentially, momenta in general, these are quantities that we define for our convenience. Okay, it's convenient to write down these formulas like that. And sometimes these momenta are conserved, sometimes they are not. Okay, so we define momenta. Okay, it's for our definition, for our convenience, sorry. So I want to remind to you guys, how would you define angular momentum of a particle? So for a particle, now I need to define a few points. So for a particle, let's say particle P, so P would be the position, the location of the particle. Let's say this is a fixed point O, okay? And there is some point A, okay? And this particle is moving. For a particle P, the angular momentum of this particle about A is what? Raise your hand if you kind of know but don't want to participate. Did anyone do any physics at all, ever? Come on, guys. You are looking at me like, what is a particle? Okay, so let's do it slowly. Do you know what a moment is? How to calculate a moment from a force? It involves a cross product, okay? And angular momentum is similar, but instead of force and moment, it will be like vector, same kind of arm from the point about which we calculate angular momentum. And instead of force, it's the linear momentum. Okay? So what is the linear momentum of point P? ROP, remember O is a fixed point, dot times the mass of that particle, let's say MP. Okay, so this is the linear momentum, and we need to do a cross product with this vector from A to P, RAP. Okay, so that would be, let's say, HP about point A. Okay, so what are we doing here? We are calculating about the center of mass. So instead of point A, we have point G. And instead of one particle, we have a bunch of scattered particles along these particles P. Yeah. For each such particle, we will do this. Yeah. So, but instead of A, we are using G, because we want to calculate about center of mass. Okay. Why are we doing that? For convenience, you will see later. Okay. In order to essentially get this. Okay. So for convenience. Okay. So what is the linear momentum of, say, one of these points, P? We need a fixed point, O. Okay, so ROP dot times the mass of that point, P, and the mass of it is rho P dV. Okay, so this one is rho P dV. Okay, this is the linear momentum of some point P, and then we need to cross it with, and the order matters, with the vector going from the center of mass to that point P. Okay, so this is for one particle P, and we need to, so this is angular momentum of point P about point G. All right? And now if we want to find the angular momentum of the entire rigid body about this point G, we would kind of sum across all of these points P in the rigid body. So we will integrate over the volume. Okay, so this is this formula. And now this total thing is equal H about G. Okay? All right. Any question? What is what? How to find G? Remember the formula from last lecture. Okay, so what we are going to do now, first of all, gradually we are going to move from this definition. Okay, so this is definition which is based on the definition for a particle. Okay, again, definition. We are going to move from this inconvenient definition, because we don't want to do every time again and again cross product and integration across the volume of the rigid body. We want to move to the more convenient representation, which is this one, where this omega is the absolute angular velocity of the rigid body, and this I about G, I'll come to it. It is the inertia tensor, or tensor of inertia, of the rigid body, calculated about point G. Okay, so this will be easier. Okay, this is a property of the rigid body, of the geometry and masses, just like this mass. And this is a not a property, this is how the rigid body moves. Okay? So this is what we are going to do first. And then later, we are going to relate H dot. This is H. Later, we are going to relate H dot to sum of moments. Okay? Okay, so the starting point is this definition. Okay? This is the top. Okay? And what I'm doing, I can go step by step just explaining mathematically what I'm doing, but it will be hard for you to imagine all the way down to I omega. So just be patient, okay? This is the math. Okay, are you okay with the definition? This is the vector from the point about which you calculate the angular momentum to the varying position point P, okay, crossed with linear momentum of point P. Terrific. Oh. Thank you. Okay, so, yep. Okay, so this is the vector from G to P, and then the linear momentum of P. So we cross them. Okay, linear momentum of P, which is the mass, rho dV, times the absolute linear velocity of that point. Okay, so this is definition, and what I'm doing now is splitting ROP dot to ROG dot plus RGP dot, similar to what we did in the beginning. So this kind of split OP equals OG plus GP. Same goes for the time derivative, the dots. Okay, so this split, is it clear? Yeah? Okay, so now I'm just kind of opening the brackets, these two brackets, and let's look at this part first. Okay, so RGP cross rho ROG dot. Okay, now what do I do here? I took ROG dot with the cross outside of the integral. Can I do that? Yes, because point G is not traversing the rigid body as I'm taking the integration. And this integration and the cross product with this vector, which is constant as I'm integrating, yeah, not constant in time, but with respect to the integration, it's like a constant. So I can take this cross ROG dot vectorially outside of the integral, okay? Is it fine? Maybe if you think of multiplying by a scalar, I can take that scalar outside of the integration. So just not like times a scalar, but a bit more complicated times and pluses, but still something constant relative to the integration. So I can take it out. And what I'm left with is this thing, which I told you, remember, it is, what is it? 0. This is integration with, it's like finding the center of mass with respect to the center of mass. Okay, so it's 0. Okay. So all of this first part goes away, and I'm left with this part. Okay, this part, I'll just copy it because I'm going to continue with it further. So just remember the beginning, H about G. We did stuff and got to integration over the volume of rho P R GP cross RGP dot dV. Okay, now this is not 0. Okay, this is not like just that first or just that first. Each of them separately would give you 0, but with the cross between them, it's something else. Okay, it's not like center of mass. So what I want to do is keep calculating. I will substitute, instead of RGP, a more XYZ components of this vector, and this one also XYZ components of this vector. So I'm going to define this vector RGP. And in order to define its XYZ components, I need a frame. Okay, so I'm going to define a frame. So let's let's look at the rigid body, and I'm going to define, so if point P, okay, so this is G, yeah, and point P are these everywhere. Okay, so if I'm homing on one of them, this vector from G to P, I want its x, y, z components along some axis. And so I'm going to define a frame. I'm going to call this frame frame lowercase g. You don't have to. So if you're going to be annoyed with the lowercase and uppercase g, instead of the lowercase g, take a different letter. Okay, and carry on. So this would be xg axis, yg axis, zg axis, and just arbitrary something. Okay, obviously later on we won't depend on a particular one. I just want to demonstrate how things look when we break down this vector into its components along some coordinate system. And what's important to remember is that this frame G, yeah, this green coordinate system, is rigidly attached to the rigid body, meaning they rotate together, okay, as if they are glued one to the other. Is attached to the rigid body. Okay, so this means that the rigid body and this frame, they have the same what? Right, the same angular velocity. Okay, so I will write here omega g, and this omega g, you know that it is both the angular velocity of this frame, absolute angular velocity of this frame, and absolute angular velocity of this body. It's important because we are going to end up with this equation, I omega. I want you to remember that this omega is the absolute angular velocity of the rigid body, okay, of the rigid body. Okay, so I'm going to define this one. Why? Because I want to get the RGP dot as well. Okay, so RGP, I'm going to define it. And then once I defined both of them, if I define this in frame G, both in frame G, I can use the golden formula, right, the derivative of a vector in a rotating coordinate system formula to get RGP dot. All right, so RGP dot in frame G, I'm also going to get it, okay, using RGP prime plus omega G cross RGP. Okay, so I just need to give you the components, how I define them. Okay, and then we will substitute everything back into where we stopped. Okay, so these are the components for the vector, not this one, for the vector from G to P, yeah, this vector, RGP, the components are Rxg, Ryg, Rzg, okay. So what are they? I need to break down this vector, yeah, onto its components along these axes. It will be hard for me, but imagine some kind of shadows. Yeah, so these are Rxg, Ryg, Rzg. Okay? for every point P that we step on during the integration, the vector from G to P has its components along the axis of the green coordinate system, lowercase g. All right? You need a break. You just what? You pause?
Yeah.
Sure. Thank you. Yeah. Thank you. Yeah. 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 No, I mean they are not moving. Sorry. Rigid body, yeah. But the rigid body can rotate. Not the same. Imagine I pin here. Okay, I put a nail. Yeah. It can still move. Changing magnitude? No, not. There is a relative velocity. Are you asking why this is 0? Yes. They both move, but they have a relative motion between them because the body can rotate. They don't. They don't become. They don't become further away from each other. They can just rotate. Same magnitude, not same orientation. Yeah. But the vector is not just the magnitude, right? The direction. There is a change because it rotates. You track that rotation. Yes. Yes. Is this from Case Friday?
Sorry?
Where did you get this from?
It's an event there for PG students. If you would like more, I can spread it.
No,
I
I
thought that
shouldn't.
it's a good refreshing for you.
Thank you.
And it's recording, I'll come back in 5.
Okay, let's go back. Now, you may be wondering why are we doing it so in depth? So I really want you to understand why I omega. If you forget, you can go back to the basic definitions, very basic definitions, and track it back. I believe that if you get the inside understanding of every little bit, you will remember it better, okay? As why is this so, and not just have some vague idea, because you don't understand why this is so right now, okay? So you're getting, you will be able to derive it only based on the tools that we are learning from scratch, right? I don't do any hocus pocus tricks, okay? I just use what we learn, all right? Okay, so I defined components along the coordinates of the green coordinate system, okay? For the vector going from G to P, remember that this vector GP is something that is going to change throughout the integration because I'm traveling across the rigid body. For each point P, I check what is this, okay, for each point P. And in a similar way, I define this omega as omega xg, yg, zg. Now, I will use these temporarily just so that you understand what's going on, and then I'll go back to only only omega and later this I. Okay, so this is just auxiliary calculation. Is there any questions so far? Now, let's look at this vector RGP. Yeah. Someone was talking to me during the break. Both G and P are points on the rigid body. They move together with the rigid body. And if you freeze the integration, not time, if you stop at some particular point P, just to try to understand what is the velocity of P relative to G, yeah, you will need to calculate this vector. Yeah, so essentially taking the time derivatives of these components. Okay, and the reason you see they are all zeros is because these are constants along the axis of this frame G, which is attached to the rigid body. When they all move together, yeah, the point P doesn't stray away from G as an observer would perceive from this green frame. Okay, so maybe just to give you some example, if this is point G and this is point P, so if I attach a coordinate system, let's say like this, xg, yg, okay, zg coming out, this vector rgp would have its components rxg, ryg, okay, and let's say in 2D nothing in the z. So when I can rotate, I can do whatever. This point is a specific point on the rigid body. This point is a specific point on the rigid body. So these rxg, ryg remain constants, remain the same, right? So they don't directly depend on time. Okay, they don't depend on time. And so when I take their derivative component by component with respect to time, I just get zeros. Okay? So this is GP prime. Okay? For every point P, there would be different components, but for every specific point P, these components would be constant with respect to time. Okay? Anyone needs me to repeat? Yes? No? Yes? So what I'm trying to explain is why RGP prime, which is RxG ddt, ddt ryg, make it square brackets, ddt of rzg, why this is all zeros. So why this is because these are constants with respect to time. Why constants? Because frame G is glued, attached, rigidly attached to the rigid body. Okay, so given any point P on the rigid body, the components of the vector going from G to P, because both of these points are specific points in a particular location on the rigid body, these components are constant. Okay? So let's say 1 and 4. Okay? So taking their derivative with respect to time directly gives you zeros. Okay, and then you need to substitute this to here, this to here for this cross product. Okay? Doing this cross product gives you this. This is RGP dot. Okay, now what is this? Now this vector RGP, yeah, it appears constant from an observer sitting on this green frame. It appears constant from here, but GP, as this body rotates and moves, yeah, because of the rotation, point P can have some different linear velocity with respect to point G. So overall, this is not 0. Okay, this is kind of omega cross R, you can think of it. Okay, so due to this rotation, potential rotation of the rigid body, this vector moves. Okay, it can have some velocity. Okay, so this is the velocity of point P relative to G, and these are the 3 xyz components of this vector in the green frame G. Okay. Okay. So what we need to do now is, when we got this result, we need to substitute this result into here, and this one also into here. Okay, so do the cross product between Rxg, Ryg, Rzg, and these 3 components of the linear velocity of P relative to G. Okay, so we need to bring it back to where we stopped. Okay, that's why I wrote it here. So this is what we are doing here. Okay, RGP, RGP dot, both in the same frame. I'm doing the cross product, and this is it. Okay, beautiful. Okay, so because we don't have so much time, from here I'm going to hop a bit faster because you can just follow the algebra. Okay, nothing very smart. Okay, so algebra, just collecting things a bit differently into vectors, kind of going to here. Okay, maybe if I shut up, you look at it, you understand faster than if I'm explaining. Just have a look. So here, rearrangement, here collection into matrix times a vector. Okay, this vector is this guy, absolute angular velocity of the rigid body and frame G. Okay, and now I'm taking the integral inside the matrix because this vector can go out of the integration. It doesn't depend on point P. Angular velocity is something that is common to the entire rigid body. I can take it out of the integration. Okay, so here it's out, and the integral goes into each part of the matrix, and this beauty is going to be the inertia tensor. Okay, so instead of all of that matrix, it's just this little I. Okay, so what is this I? Again, I lost my cursor. Okay, so all of this matrix will be the inertia tensor, this one. And, okay, this G here, this G, it's a G, by the way, if you need glasses. Capital G, this capital G is about which point you calculate this inertia tensor. How does this G, how do I know it's this G? Because of all of these R, YG, R, ZG, and so on. Where do they come from? These R, YG, R, ZG, R, XG, they come by defining this vector from G to P, always from G, right? So for this integration, I'm taking these R positions, these components, for the vectors going from G to all of these points P. Okay, so G is my kind of origin. Okay, capital G. And then this lowercase g, yeah, this one on the left, like for a vector, this is in what frame I'm working. The green one here. I'm taking these components along the axis of the green frame G. Okay? Now, any questions so far? What I need you to remember is how this looks. I need you to remember it by heart. Okay, this is one of the formulas you need to remember. In the next set of slides, we are going to, this is lecture 11. In lecture 12, I'm going to give you examples of different inertia tensors for different rigid bodies, different geometries. These ones, like the results, I don't expect you to remember. But how to find? Yes. Okay? Yeah, this one you need to remember. I thought I was clear. It's not hard to remember, right? You remember much more complicated things. Let's say your timetable. Your timetable has no symmetry. This one has symmetry. Okay? Okay. There's just a handful amount of formulas you need to remember, and this is one of them. Okay, trust me, it's not a memory test. It's not. Okay, it's an understanding. Okay, if you go through the calculations, if you spend 1 minute looking at that, you'll remember. Okay, just 1 minute. So just spend that 1 minute. Okay, we end up with this formula, which is this one that I promised. Yeah. Okay, what is this omega? This is, how do you call this one? Right, absolute angular velocity of the rigid body. Okay, now you see here it doesn't appear with this lowercase g. Why? This lowercase g is arbitrary. I just used it so that you can see how to come to this form. But I can choose, obviously I can choose this green coordinate system to my liking. Yeah, I can choose any one. And in particular, I just wrote here another way to write it. So this h is a vector. Again, it's a vector. I can represent it in any coordinate system I want. And I can transition from h in frame G, like at the top, to h in another frame, F, by just using a rotation matrix from G to F. Okay, this is all good. Okay, all allowed. Okay, so angular momentum you can calculate in any frame you want. This is a vector. Listen, this is a vector. You can represent this vector in any frame you want. Okay. If you want to move from omega from frame G to another frame, you just rotate by a rotation matrix. This one is not a vector, it's a matrix. Okay? So don't just pre-multiply it by a rotation matrix to get it in another frame. It won't work. We will learn what to do to kind of rotate inertia tensor to another frame. Okay, it's a bit more complicated than doing this operation. This is good for vectors, not tensors, not matrices. Okay, so don't apply this just on I and just on omega separately. Don't. Okay, but for the entire thing, yeah, for this H, the product, you can. Okay, so this is something that many students get wrong. But in general, sorry, as long as you multiply I and omega in the same frame, if I is in some frame and omega is in the same frame, you can do the product and get H in that frame. Okay, so the only thing you're missing is how to get I in a different frame. Okay? But you can think about it. It's not complicated. So for inertia tensor, just a brief conversation about that, and we'll come to it later. The name tensor of inertia, now I'll just say it now. I never said that before. And then students get it wrong. I defined something called inertial, roughly. I speak about frame 0 often as a frame that doesn't rotate. And I call it sometimes inertial with L at the end, inertial frame. Okay? This is something called tensor of inertia. Inertia is like, I don't know, mass or something you carry as you move, something that objects motion. This one will essentially object rotational motion as mass would object linear motion. Okay, we'll go into the meaning of that later. Just don't call it inertial tensor. Now, not invariant of frame means it will have different values in different frames. Okay, so pay attention to which frame you are calculating your inertia tensor. And this is the names of the components along the diameter. Diagonal. They are called moments of inertia. So moments of inertia are these IXG, IYG, RZG stuff. Okay, and these ones are always non-negative. Okay, non-negative. Now these ones, IXY, IXZ, IYZ, and so on, they are called products of inertia, and it is common to place them here with the minus sign, because by definition you have the minus sign before the integral, so you keep the minus sign here. All right, maybe some textbooks do it with the minus, some without. Okay, so remember as you wish. Okay, eventually you need to remember this one. So, yeah. I will refer to products of inertia as the I's here, without the minuses. Okay, so these products of inertia, they can be either positive or negative or 0. Okay. Could you close, please? Thank you. Okay, and notice that this inertia tensor is symmetric. It being symmetric is a property that we are going to utilize later when we are talking about principal axis. So it's important. You remember it's a symmetric matrix. All right? Okay. Now, what we are going to do is relate H dot to the sum of moments. So we spoke about this part first. Now we are going to this one. Okay, so it's a similar derivation like here with the idea of the internal and external forces. Okay, so let's look at the maths. Okay, now this one this guy here is what? Angular momentum about point G by definition, just by definition, and I just plugged this G in here. You know what? All of this thing, all of this slide, the left lowercase g, you can ignore it. It's good in any frame. Okay, so I should probably get rid of it. But anyway, so this is by definition, okay? And now what I'm doing, I'm taking a time derivative, okay? When we did it for this one, it was more straightforward, okay? So r dot became r double dot. Okay, here we have a cross product between two values, and when we take the time derivative of a cross product, if you think of a cross product as taking components and kind of meshing them by multiplication and summations or subtractions, if you think of it like that, when you take the derivative, you need to use a derivative of a product, okay? The rule for a derivative of a product, even though it's a cross product, it will still work, okay? So I'm using derivative of a product. So first I'm taking the time derivative of this one, so from RGP to RGP dot, and then here, and this part unchanged. I want to be a good weatherman. I need to. Okay, so this is unchanged, and then now here this is unchanged, and here this is the time derivative of this one. Okay, so this is derivative of a product, and then from here ROP dot, I split like before, ROG dot plus RGP dot. Okay, same summation, and then I open it up to open the brackets. Yeah, so this one here, what did I do? I took ROG dot outside the integration. Can I do it? Yes. G doesn't depend on P. All right, so I'm left with this guy here. You should already recognize this is 0. Cool. This part is, yeah, this cross with this. Okay, and what is this thing? RGP dot cross RGP dot. It's 0 as well. It's a cross product between parallel vectors. Okay, in this case they are even equal, and that's why it becomes 0. Okay, cross product of same direction. And this part, what did I do? I changed the R. If you think of the ROP double dot as the acceleration of point P times rho dV, the mass of point P. So this is the MA. Yeah, this is the MA, so sum of forces on point P. Okay, sum of forces on point P, and then cross with the vector from G to P. Okay, so that would be the moment on point P relative to point G. Okay, maybe I'll bring it back here. So G, and here is some point P, and remember there are the external forces and the internal forces acting on it roughly. Yeah. And so this vector, let's say overall, let's say this is the sum of forces for point P. So this is the resultant of all of these ones. Yeah, the total one. So I'm doing cross product between R, G, P, and this vector of the forces acting on this particle P. Okay, so I will get its arm vector cross, it's called, I think, moment arm. Yeah, cross the force gives you the moment. Okay, and then just like before, all the internal forces, they would kind of cancel each other throughout the integration, and I can only consider eventually the external torques or moments about point G acting on the entire rigid body. Okay, so when I sum, if this is G, the rigid body, there are the external forces acting on it, and you should also consider pure torques or couples. I don't know how to draw them. Maybe maybe, yeah. Oh, sorry. Change of mind. So something like that would, with double arrow, would represent pure torques. So overall, you would sum these pure torques or moments and take, say, if this force is acting on this point, or lines of action, you go relative to G, you go the vector from G to that point, cross that force, and you sum all of them. You're puzzled, sorry. So I essentially need to sum all the moments, external moments, on the rigid body. Okay, so if this is, say, tau 1 vector, tau 2 vector, tau 3, yeah, F1, F2, F3, F4. Yeah, try to recall mechanics, okay, wherever you summed moments. So it would be tau 1 plus tau 2 plus tau 3, which are pure moments or torques or couples, okay, plus, and I'm doing it about point G, so I would take the vector from G to, say, let's say P1 cross with F1 plus RGP2, yeah, if this is P2, cross F2, and so on. Okay, so I'm taking into account all of the external moments acting on the rigid body. I will give you examples later, but in general, you should recognize roughly what I mean by sum of all the external moments about the center of mass, G. Okay, about the center of mass. It means that all the forces acting on this rigid body, I'm taking the moment arm relative to this point G. You look so puzzled. Is it complete unfamiliar area? Sorry? Is it just Friday, end of day, or yeah? So please, well, after the lecture, go back to your background. When you wanted to, say, find equilibrium equations, you said all the forces are zero, all the moments are zero, right? How did you do the moments? you had some pure torques potentially if something tried to rotate a beam or something like that, and if there are some forces applied on some body, right? I don't know if you did trusses or something. I'm not the first subject you're taking in engineering. You should have done some cross products like that. Maybe because everything in 2D by chance? Yes, no? No. So if it wasn't in 2D, you should have done cross products. Okay? Anyway, we'll come back to it. Is it clear how this is the last survivor? Yeah, so H dot about G is equal to sum of moments on the rigid body about G. Okay? Now, I'm going back. I'm going back here. Okay, so this equation is the start and end here. Okay, is it clear? Can you follow? Yes, on the weekend. Okay, let's say you at least identify this is the left part here, okay, and the right part. Okay, at least you identify where to look for the details. Just please notice this was done, this calculation, everything here was done about the center of mass. Why am I saying it? It's important because we said, for instance, this becomes 0, but this is 0 vector only when this G is the center of mass. Otherwise, it's not 0, right? So we use the property of center of mass to ignore this part, right? So it's not like we can do it for any point, okay? Not for any arbitrary point. We are going to get this equation, okay? Which is a very common cause for mistakes, not only to students. I've seen like lecturers in other departments doing this equation, but for a point which is for which it's not correct, okay? Some kind of general point. Okay, so you can't just assume any point here. Now we are going to do it for another case later on, but for the time being, just pay attention where we took the assumption that G is the center of mass. Okay. Now this is a summary slide. Okay. This equation is what? This kind of simplified definition of angular momentum over rigid body. This omega here is the angular, the absolute angular velocity of the rigid body. Okay. If you don't remember anything else from this lecture, this is what you must remember. This is the angular velocity of the rigid body. Okay? Now this is h. You will need h dot. In order to construct the angular Newton-Euler equation, you will need h dot. How do you do the dot? You go to the golden formula, right? The golden formula has its own omega. This omega is the absolute angular velocity of the frame in which you take the derivative. Okay? And you can transition between h in one frame, h in another frame, using rotation matrices, or h dot in one frame and h dot in another frame, using rotation matrices. Okay, so I need you to understand the difference between this omega that is not necessarily related to the rigid body itself. Okay, it could be because this frame F here, this frame F could be some arbitrary frame that is not attached to the rigid body. Okay, so this would be the angular velocity of that frame, whereas to define angular momentum of a rigid body, you will need to characterize the motion of that rigid body using the angular velocity of that rigid body. Okay? Okay, so this omega in the definition of H is for the rigid body you are calculating this for. So maybe I'll do a summary of, I think it appears on the notes on LMS, but this is about which point you calculate the angular momentum. This is, say, which rigid body in the system, just the label, because you can have body 1, body 2, body 3, right? And this is in which frame you represent the components of this H. Okay, so maybe I'll write it here. About which point. This one is of which rigid body, or particle, and this is in which frame you represent the components. Okay, now this is angular momentum of some rigid body. So when I say it is equal to I omega, again, omega is of the rigid body. Okay? If you want to calculate the derivative of H in time, the true time derivative, the change over time of angular momentum that you will need for the Newton-Euler angular equation here, yeah, you will need to use the golden formula like we learned last week, and you can do it in any frame. Okay, so you can just represent your H in some frame, okay, and use the golden formula correctly with the angular velocity of that frame. Okay. Okay. Now let me just start the next lecture, and we are starting to have a delay, but it will close. I will close that delay because we are having an extra lecture. So don't worry, we are still ahead of tutorials. So let me just start. This one is not hard. You are laughing because you don't believe. Oops. Okay, so essentially, there are a few examples here. Oops. So it's stuck. In the meantime, you know what you can do? Write down that big matrix of inertia tensor with all the integrals. Practice this one. Okay. Whew. Okay, so this lecture covers just a few examples of calculating inertia tensor for a specific geometry. Okay, so we put aside the dynamics, the motion, and just look at geometry, evaluate those integrals. Just like with center of mass, when we looked at the triangle, we put aside the dynamics and just looked at geometry. This is the same, okay? This is like a side branch. So what we are going to cover is everything is find inertia tensor 4. For cuboid, okay, is a simple shape, okay, and the coordinates you are integrating over are Cartesian coordinates, just x, y, z, simple. And then cylinder, I'll just state again, you don't need to remember the results by heart here, okay? These are examples of how to carry out the integration, okay? You should remember the basic formula, this one, and be able to construct the integral with the correct limits and the integrand inside, okay? But you shouldn't remember the results for particular geometries. So for cuboid and then for cylinder, we are going to work with cylindrical coordinates. And then for a torus, why do you need a torus? Because you will need it for, I don't remember, maybe for assignment too, but also for the lab, because I wanted you to model so you see these rings, their shapes are like a torus. Okay, if you don't know what the torus is, I'll show you. What's the plural of torus? Tori. Tori in the English pronunciation. Good. Okay, and then this one, cuboid with cylindrical holes. Okay, what we will do is apply which principle? Superposition, kind of. Okay, you can think of it as similar to the example with the holes in the triangle. Okay, so this is because now we are doing it all in the same day, but normally in previous years it was different days, so I need to remind. Okay, this is the definition of inertia tensor about the center of mass. Okay, and I need to pick some coordinate system in which I will define these r xg, r yg, r zg. Okay. If I pick a different coordinate system, I would get different values here. Okay, so I need to specify in what coordinate system I'm finding these values. And also, this is, remember, everything is calculated relative to the center of mass. Okay, okay. Okay, so for a cuboid. Now, I'm not going to do each of the 6 different values. Okay, I say 6 because it's symmetric. I'm going to show like one example for a moment of inertia and one example for a product of inertia. Okay? So for a moment of inertia, I pick the xx. Okay? And by the definition, I'm using, well, this is all kind of by definition, except for the limits of the integration. Okay? Sorry? Why are the limits between, say, for z, why are they between minus c by 2 and c by 2? Because your point P, as it travels across the volume, I'm kind of going, I'm going first in the z direction, in all the y directions and the x directions last. Okay? So as I'm going along the z direction, I start from c over 2 below g, and I end with c over 2 above g. Can I do from 0 to c? I cannot. 0 to c would mean my reference point is on the ground of this cuboid, so I cannot. Okay? My value for RZG is relative to point G. Okay, it's from G to P. And the values would go from negative c by 2 to positive c by 2. Okay, if you will do from 0 to c, you will effectively calculate with respect to another point on the bottom of this cuboid. All right? So let's continue from here next time. Okay, I'm sorry we got some delay. And thanks a lot.
Yeah, I was just wondering about that. So the rotor, so in the question it says the rotor is rotating. So can we like create another reference frame for the rotor specifically?
Yes.
Because that way you can get the angular velocity of the rotor with respect to itself, which is a lot easier. This is just delta dot in z-axis, and then rotate it in the correct frame.
Yeah. So you can attach frame 4 if you like.
Right.
Or you can even calculate angular velocity of the rotor relative to the frame directly in frame 3 without even finding frame 4. But you can do frame 4, yeah. Especially if there is this kind of point P.
Right. Because the only part about the question that was confusing is which one of the surfaces is the rotor. Then after you show us what the gyroscope looks like, it makes more sense. All right. Thank you.
Is there any possible way to check if I'm getting the right answer, like just by observing if it's negative? So just for like cross reference. So is there any method to check if I'm actually doing it the right way or not?
I'm sure there would be some genius who will see through it. I don't care about values. When it comes to substituting values and getting a number, it's so random. It's cosines and sines of radians, and I don't know like what's radian